Hi everyone, my name is Claire Tomlin. I'm a professor of electrical engineering and computer sciences at UC Berkeley. And this is the 19th module in a series of modules that we're recording to support the course EE221A, Linear System Theory at Berkeley. In this module, we're going to be discussing the solution to the linear time varying system. And if we recall, in the last module, we presented a piece of that solution. We presented the state transition matrix. So let's just recall what the state transition matrix is. It's given as the solution to the following matrix differential equation: x dot of t is equal to a of t x of t, where now in this case, in this matrix differential equation, x of t is a matrix. So it's a matrix in R n by n, and of course a of t is our n by n matrix. So the solution to that differential equation, starting at an initial condition, which is the identity, is defined as the state transition matrix. And we recall that we use the notation phi of t comma t0 to indicate the value of phi at time t, given that the system started at time t0. So it's defined to be the solution. There's only one solution to that differential equation for any given initial condition, because it's Lipschitz continuous in the state and piecewise continuous in time. So it's the solution to this following matrix differential equation, MDE for the matrix differential equation, starting at an initial condition, so x at t0, which is defined to be phi of t0 comma t0, which is the identity. So in particular, this means that this is the value of phi at the initial time, given that we started at the initial time. So from this really definition, if you started at time t and you look at the solution at time t, then that is the identity. So that's part of the definition of the state transition matrix. And we showed last day a few properties of the state transition matrix. In particular, we showed that if we go back to the vector differential equation, so now this x, it's meant to be little x, but it's a vector in Rn. So the matrix differential equation, which we've been discussing quite a bit, so here now x of t is a vector in Rn, and a of t is the same n by n matrix that we've been looking at. The solution to that matrix, or to that vector differential equation, starting at an initial condition of little x0, a vector in Rn, is given by x of t is equal to the state transition matrix for a of t multiplied by the initial condition. Okay, so whereas the state transition matrix is defined in terms of the solution of this matrix differential equation, we then can apply it to this vector differential equation and compute the solution as follows in terms of the state transition matrix. And we check that the dimension agrees. So phi, of course, because it's a solution to this in place of x. It's an n by n matrix, and x0 is an n by 1 vector, so it gives us our solution in terms of this vector differential equation, which is an n by 1 vector for any point in time. Okay, so, and we discussed properties of the state transition matrix last day, but now let's go back to our original linear time varying system, which is given in terms of a state vector x and an input vector u. Okay, so our original system is given by x dot of t is equal to a of t x of t plus b of t u of t. And we recall the dimensions, so x is a vector in Rn. We'll assume we have multiple inputs, so u is a vector in Rni for any given point in time. U belongs to Rni. So A is an n by n dimensional matrix, and B is an n by ni dimensional matrix. And suppose we start again with an initial condition, x at time t0 is equal to x0. So our claim, or the theorem, is that the solution, the solution to this is our differential equation. I'm just going to call it DE for differential equation, and we'll call the initial condition IC. So the solution to that differential equation, initial condition pair, again, there's only one solution for a given initial condition because the right-hand side of the differential equation satisfies the conditions of the existence and uniqueness theorem. It's Lipschitz continuous in X and piecewise continuous in time. So the solution to that is given by the following: X of t is equal to the state transition matrix for A, phi of t comma t0 times x0 plus the integral from t0 to t. So this is the component, the contribution to the solution from the initial state. And now we have the contribution from the input, phi of t comma tau, b of tau, u of tau, d tau. So tau here is our dummy variable of integration. Okay, so how do we prove that that's the solution to that differential equation? Well, since there's only one, we know there's only one solution for a given initial condition. All we have to do is check, as we've done in our exercises before, that this candidate solution satisfies the differential equation and the initial condition. And that's always easy to check. So, well, first of all, the initial condition is always trivial to check. If we check, so this is the proof of the theorem, but we're first going to check the initial condition. So check that x of t0 is equal to x0. So what we do is wherever we see t, we plug in t0. So that's phi of t0 comma t0, which is the identity by the definition of the state transition matrix, times x0 plus the integral from t0. Again, wherever we see t, we plug in t0. And now it doesn't matter what's here because we're integrating the integrand over 0 time. So the contribution from the integral is just going to be 0. And we end up with the check that the value, this candidate solution, is x0 at the initial time. Okay, so to check that it satisfies the differential equation, we're going to have to take the derivative of this expression. So it requires us to take the derivative of phi, so we'll use our properties of the state transition matrix. But it will also require us to take the derivative with respect to time of an integral where both the limits of the integral, this one doesn't, but this one does, and the integrand itself depend on the variable that you're taking the derivative with respect to. So in order to do that, we recall how we take derivatives of integrals. And let's write that up here. So we'll erase everything except the candidate solution. And we recall, it's called Leibniz rule for taking the derivative of an integral. And so we'll give it in terms of dummy variables. So the derivative with respect to the variable z of an integral where the limits on the integral are a of z, b of z, and then the integrand is some function f of xz. So it also depends on the variable that you're taking the derivative with respect to, dx. So here z is t and x is equal to tau in our case. It's given by the following. So it's the value, the derivative of the upper value of the integral, db by dz, times f of bz, minus dA by dz, so these a and b are possibly functions of z, times f of az, plus the integral, and now we bring the derivative inside the integral from a to b of f, so we're bringing the derivative in, so d by dz of f. And f is a function of x and z. So we'll write that, and that's just, again, dx here. Okay, so we have a term, we have three terms, depending on the limits of the integral and then the integral itself. Okay, so how do we apply this to the system? We're now going to check that it satisfies the differential equation. So we'll erase the initial condition check, check the differential equation. Okay. Okay, so the derivative x dot of t is equal to, so the derivative of phi, so this term here depends on t only through phi, so it's a of t, phi of t, t0, x0, plus the derivative with respect to time of that integral. So the first term is dt by dt, which is just equal to 1, but we'll write it down, times f, wherever we see the value tau, we plug in the upper limit t. So it's going to be phi of t comma t, b of t, u of t, minus dA by dz times f of az. Well, in this case, the lower limit is t0. It's fixed, and it doesn't depend on time. So that term just goes to 0, and then we end up with the integral term, which is the integral from the limits t0 to t of df by dz. So now we're just taking this derivative here with respect to t. So we pull out the a of t, phi of t tau, b of tau, u of tau, d tau, just remarking here that the only dependence of that integrand on t is in the state transition matrix. All the other variables here are tau, and we're taking the derivative with respect to t. Okay, and now we can simplify. So this is equal to 1. This is the identity. So the contribution from this term is just b of t times u of t. And then we can factor out the a of t from under that integral because it doesn't depend on the variable of integration, which is tau. And so this is just equal to a of t. So we'll factor it out from both terms. And then we've got the contribution from the initial condition and the contribution from the integral, the input. Phi of t tau, b of tau, u at tau, d tau. Okay, so we see immediately that we've recovered inside the square brackets our candidate solution x of t. So indeed, x dot of t is equal to a of t x of t. And we've shown that it satisfies the differential equation. Okay, so what have we done here? We've proven that the solution to x dot is equal to a of t x of t plus b of t u of t, initial condition x0, is given by the following formula. Okay, very important formula, but as we might suspect, in general, it's hard to compute because it requires knowledge of the state transition matrix phi. All right, so we have to think about how, in what situations can we compute this state transition matrix easily? And so that will be the topic of future modules. Thank you.